Good. Today we'll be talking about a project simulation. I have simulated a simplified team, and there are some surprising results we can see from this simulation that we can take back to our work and understand why our software teams are working the way they do. There are two audiences for this video. The primary audience is anyone who is interested in project management. A technical background is not necessary. You could be a CEO, a head of marketing, a head of sales, any kind of business person. The secondary audience is someone who understands coding. I'll show you the code that I've written to simulate this project, and I'll identify that so that you can clearly skip to the next part if you don't understand coding and still get most of the value from the video. With that in mind, let's get started. So assume there's a simplified team consisting of only one engineer. His productivity is 0.5 tasks a day. That is, on average, he completes half a task in a day or one task every 2 days. And this is average. Some tasks may be done very quickly, maybe in an hour. Some may take a week. But if you average it all, the productivity is 0.5 tasks per day. And new tasks are created at the rate of 0.5 tasks per day. So the engineer, his input comes at this rate and his output is also at the same rate. But both of these are random. So let's see how that works. I'll first show you the code. If you're not technical, click the next chapter below in the video and you can skip to the part where we discuss the results of the code. So let me show you the code. This is the entire thing. There's a backlog, which is how many tasks are not done. Those are these new tasks over here. Then completed tasks. Both are 0. And we simulate the project over a year. There are 221 working days over a year, and each day will run the simulation, right? First, and by the way, even if you are non-technical, I'm explaining, so you will be able to get the gist of it. First, on a given day, we randomly have 0 or 1 new task added to the backlog. Then, on a given day, the engineer completes either 0 or 1 tasks. The only thing to keep in mind is if the backlog is empty, then the engineer cannot complete a task, right? So the engineer is sitting idle, wasting his time on that day. And you calculate two measures for this. One is the productivity, which is on average how many tasks per day is he completing. Ideally, it should be 0.5. The other is the backlog. How many weeks worth of work remains? Why does the backlog matter? Because you often end up in a situation where work takes weeks or months to get executed and people complain. Whenever I make a request to the engineering team, it takes weeks or months to get it done because the engineering team is already swamped. So that's the backlog. Now, for each day, we print out these two metrics and I put them in a Google Sheet. I've run the simulation 3 times. This is the first, this is the second, and this is the third. We'll start with the first simulation. And as the days go by, the productivity is changing and the backlog is changing. The backlog is in weeks. So let's look at the productivity first. These 3 colors are the 3 simulations, as you can see here in the legend. Simulation 1, 2, and 3. And you can see that the average productivity ends up at roughly 0.5, but a little lower, 0.42, 45, or 48. Why is the productivity not exactly 0.5 tasks a day? Because we lose some days by not having an engineer, by having no task available when the engineer is idle. And also there is some randomness. So this productivity is a random number, right? Over a big sample set, it converges to this, but for just 221 tasks, there will be some error. And even here, you notice it converging. If you look at the yellow line, it's converging here. And if you look at the blue line, temporarily the productivity exceeded 0.5. Maybe because there were many tasks that just happened to be done quickly by chance. But then over time again it's converging. So this is the productivity. The second thing is the backlog of weeks. So if a new task is assigned today, it's put in the backlog. All the existing tasks in the backlog need to be done, only then the new task will be done. So how long will that take? That is the backlog. And you can see in one case the backlog is 0.4 weeks, which is 2 days. Now, which is not bad at all. In the second case, it was 2 weeks, which starts to make people uncomfortable. And in the third case, it was 8 weeks, which is like 3 months or so, 2 months, which will make people really uncomfortable and unhappy with the engineering deliveries. So you can see how different simulations behave in different ways, because they are all random. And if I continue this blue simulation, which looks very good, it may go up, just like the yellow and the red went up. In fact, the blue itself was high earlier, 3.6 weeks, almost a month. So one thing you need to understand is, if you look at it at a point in time, it may be abnormally better or abnormally worse, but over time it can change. And also different simulations behave differently. This is why if you are simulating any system, you shouldn't just run one simulation. You should run multiple simulations, and you can see how things vary. Otherwise, you will just, if you run just one simulation, you may say, hey, this is how it is. It's not bad. It's 0.4 weeks. But that was just that simulation working that way by chance. So that's why you should run multiple simulations. This is called the Monte Carlo method. Basically, the idea is simulate a bunch of simulations, for lack of a better word, and see how it behaves, not just one. These are the sheets of the raw data. So this backlog is in weeks, and this is tasks per day. Let's see if there's any other takeaway from this. Just give me a second. Yeah, this is another project simulation. In this case, we have a sequence of workers, not one engineer, but a sequence of them. These two are still the same. The productivity for each engineer is so much, and the rate of creation of new tasks is so much. The thing that changes is, instead of one engineer, you have a whole bunch of engineers. And bowl 0 is the input bowl. The first engineer takes a task from this bowl, completes it, and puts the result in bowl 1. The second engineer takes it out of bowl 1 and puts it in bowl 2, all the way till bowl 9, which means there are 8 engineers in this simulation. And you have the productivity as well as the inventory or the backlog, which we called earlier. Let's see how the simulation performs. Here, I think we have run one simulation. Let me look at the, yes, this is one simulation. And again, you can see that the productivity goes to 0.5. Earlier, we ran 221 iterations or 220. Here, let's see how many we have run. We have run 5,000 iterations, which is why you look, this is smoother than this, which is still very noisy. So when you keep running more and more iterations, it becomes smoother. The inventory is pretty bad. This is the code for the second version. Again, if you are not technically inclined, please skip this chapter, go to the next chapter. You have a bunch of bowls. Bowl 0, let me scroll to the top. Bowl 0 to bowl 9, which is 10 balls. And you have this function, you generate a random number, you put it in the first bowl. So dest index is the index of the bowl to which you are moving. So if you are moving some task from the third to the fourth bowl, dest index would be 4. And if dest index is 0, you just put it in the bowl and return. Otherwise, you calculate source index, which is the previous bowl. And then again, you can't move more tasks than we have in the source bowl. So the source bowl is empty, we can't move a task. And you transfer it. And you perform an iteration for all the bowls. So first you move something to bowl 0, then bowl 1, then bowl 2, all the way till bowl 9. So all that is done here. So this is one iteration. And you perform whatever 10,000 or 5,000 iterations. Excuse me. And here the backlog is a number of tasks, not the days. In the previous simulation, this backlog, it was weeks, sorry. Here, this backlog was in weeks, you can see here. In this, it is in tasks. So when we say that there are 38 tasks, that means on average it should take 19 days. So here it's measured in tasks in this simulation. So as you can see, the productivity starts off pretty bad and very quickly increases, then slowly increases. The inventory keeps shooting up till 216 tasks, which is very bad, which is 108 days of work, which is 4 months or so, 5 months. So in this case, inventory has built up faster. This is what is going on when you have a software team where the team feels under siege. People are demanding more and more from the team. And the people who want the task done are very unhappy. They are saying nothing is getting done. And they lose trust in the engineering team. They start pinging the engineers again and again out of frustration and helplessness. Is it done? Is it done? Is it done? The engineers keep getting fed up. I'm trying to do work and these people are pinging me. So the engineering team loses credibility in the eyes of the business people. The business people lose credibility in the eyes of the engineers. They are perceived as an annoyance rather than a partner. So the relationship often breaks down from both sides. And this is what is going on in the background. That's why I'm walking you through this simulation. So here, the productivity is not a problem. It's what you would expect. The inventory is building up. And even here the inventory has, the inventory or the backlog has built up. Why has it built up here? Or there, the logic is the same. Because if you look at this, whether you have one engineer or multiple engineers, the logic is the same. Because if the productivity is more than the rate at which new tasks are assigned, suppose the productivity were 0.6, then this will not go up in an uncontrolled manner. Because if you are doing work faster than the work is coming to you, the backlog will not keep growing forever like this. But that's not the case. So it keeps growing. And we can look at each of the bowls. The inventory is the inventory in all the bowls. So if you have 2 tasks in each of the bowls, then that's 2 times the number of bowls, except the last bowl, which is the output. So bowl 1 goes up till 60, bowl 0, bowl 1 goes up 65 to 29. So this may give you hope, but it's often a false hope. If you continue running the simulation, it will shoot up again. Bowl 2 is worse at 38. Bowl 3 is similar. Bowl 4 is, this is much more chaotic. Bowl 5 is again chaotic. Here it becomes worse, 645. Again, this is lower. This is the output bowl, where all the tasks eventually end up. And this should grow because this is the output of the team. If this is not growing, the team isn't delivering. So this should grow. Whereas these should not grow because these are all partially done tasks. And they don't add value to the team. In a factory, you have inventory, which doesn't add value because you can't sell it. You have invested time in purchasing the raw materials and in doing part of the processing. So if you take a car factory, let's assume for now that all the components of the car are being made in-house, such as the tires and the engine and the brakes and so on. If you have 1,000 engines that are assembled, but the rest of the car is not yet available, the raw materials that go into these 1,000 engines, as well as the processing that was put in to create the 1,000 engines, all the machines, the electricity, all of these, the workers' time, all this investment has been made, but you can't sell the engine by itself. So it is money that is locked up, which you don't want. The same thing happens in software. Here the factor that causes the cost is the engineer's time. So if you look at all these bowls, let's take bowl 8, which is the penultimate bowl. So if something is in bowl 9, that's good, it's completely done. The car is ready, you can sell the car. If something is in bowl 8, it's not ready yet. Maybe the car has everything except brakes, so you can't sell it. Now if you look at a random number, trying to find a high number, max is 21. Okay, just scroll somewhere. Okay, let me take this number 16. After 2500 iterations, there are 16 items in this bowl and 23 in the previous bowl and 2 in the previous bowl. So if you look at these highlighted cells, these are all partially assembled cars. The first row is backlog, nothing has been done on it. Backlog doesn't incur a cost, but these things in blue incur a cost because to get something to these columns required lot of time from engineers. And there is no result because you have partially assembled the car and you can't sell it. This is good. Column J, because the final result is ready. The feature has launched in software, which is the equivalent of the car being sold. The feature has launched, people are using it. The customers are happy, hopefully. So this is value to the customer. This is just a backlog. The things in the blue are things that have incurred a cost. And if you take the sum of all of these, 109 tasks, see how big it is? 109 tasks have been partially worked on. That's a huge amount of inventory. Money is locked up. And what are these bowls? So assume different stages in a company. So first, let's say a marketer identifies features. That goes from 0 to 1. Then maybe a PM. Then maybe a UX designer. Then maybe a back-end engineer. Then maybe a front-end engineer. Then maybe a mobile engineer. Then DevOps. Then QA. Then it's launched. So those are the sequence. Now, in a real team, there is some amount of parallelization The back-end and the front-end engineer can typically work in parallel. But in this simulation, we are assuming there is no parallelization at all. It's a strict assembly line. The fifth person can start work only after the fourth person has finished work. That's what we are assuming here. And this backlog is exactly why you should prioritize. One critical thing that needs to be done, when I've worked with a lot of companies where the backlog is getting big and things are not getting done, I always tell people, prioritize, prioritize, prioritize. Because people tend to look at each task in isolation. They say, I want this, I want this, I want this. That doesn't get you anywhere. Each person should prioritize his or her own requests. So if the head of sales, let's say, wants 10 things to be done, there should be a priority. She should maintain her own priority list. Let me just try to create a simple spreadsheet with multiple tabs. Salesperson's requests. And here you have A, B, C, D. Right? The salesperson or the head of sales can prioritize however he wants. It's his priority. Then there's a separate marketing request from the marketing team to the engineering team. And they can have their own priority. So people should never say, I want this. And if the marketer comes up with a new task, let's say Z, she should decide where in the priority it goes. She can't say, I want Z. She has to decide where it goes. Does it go to the end, which means it's the least priority, or does it go to the top? Either is fine, but not prioritizing is not fine, because then you get stuck in this huge backlog and everything can't be important. So when you don't prioritize, it creates another problem as well, which is from the engineering team's point of view, the business people come across as changing their mind. They ask for Z this week, then U next week, then K, then Q, then M, then L, then P. Every week there's a new request before the previous one is done. This appears to the engineering team as this person doesn't know what he wants. He keeps changing his mind every week. So just ignore whatever he's saying. After a week he'll forget it and ask for something else anyway. Of course, that's not a healthy dynamic for the team, which is why each person needs to prioritize. Anyway, hope this was useful. If you'd like me to make your team run more efficiently and not have a backlog of an year, my consulting link is in the description.